Thank you very much. Now, Paula said I have a background in mathematics and philosophy and in cognitive science. I actually did some programming when I was a young student. I wrote a theorem-proven program in Lisp as a kind of master's exam, but that's a very, very long time ago. Anyway, I will talk about some kind of, I don't know, epistemological or ontological problems around AI, how we represent information in AI systems. And holistic AI means that it's a system that can both use reasoning and categorization and communication. I mean, it's a pipe dream. I'm not going to present you any concrete results or anything like this. I've been working with a group in University of Technology, Sydney, and this is their rather funny logo. And so some of these ideas have been developed together with them when I was there some time ago. So the main idea is what is an event board, but I'll get back to that. Let's start with the beginnings of AI. And in the early 60s and 70s, you had everything was symbolic representation. All programs were written in first-order logic, in some programming language. Robots were programmed in first-order logic, and it didn't go very well. You very quickly came up against the frame problem. And the frame problem says that if you want to describe the environment for a robot using sentences, you end up in a very, very complex system. And the complexity grows very quickly if you want to solve practical problems. So the frame problem stopped that kind of using symbolic representations in robots. Of course, you still use it for all kinds of other programs. Later, this kind of constraint given by the frame problem has changed into a work on formal ontologies. You try to describe the world in ontological structures, but still within some kind of logical framework. And lots of people are working on these formal ontologies. But still, I mean, the basis is still first-order logic there. The second flavor of AI began to appear in the 1970s. That's machine learning using connectionist system, neural networks, and things like that. And at the beginning, these systems were not talking very much to each other. But neural networks, they have to be trained and trained and trained, and you don't know, they are biased, you don't know exactly how they learn, they're data greedy, they're opaque, you don't see what they do, and they are brittle. That is, small changes may lead to drastic changes in the results. But there were some progress in machine learning, and it's a very big area nowadays. Then some people working in AI try to combine these two traditions to have something that is called a blackboard architecture. And that means you have some kind of symbolic system that is doing some kind of reasoning. Then you have some kind of machine learning system that doing categorization, maybe some other tasks. Then you put all the results on a blackboard, and then different processes can take in information and then put them back on the blackboard. So that was an architecture. It's a kind of hybrid architecture between the symbolic and the... And there were some systems developed for this. Unfortunately, I mean, I don't know very much about it, but there was no, let's say this was a programming solution. There was very little discussion on the semantics or the ontology or what was really happening on the blackboard, what was going on in terms of the meaning of things and so on. So it was a solution that gave some result, but didn't go very far. So these are my critical points against the two dominating traditions that have been going on in AI. Now I want to become a little bit more constructive, and I want to use my theory of conceptual spaces, and in particular using conceptual spaces to represent events. And I'll try to explain to you in a while why I think events are interesting as a kind of central form of representation for an AI system. This is my key idea here. I haven't developed it, as I said, but this is just to give you an introduction to how I think an AI system should be structured. So, first of all, a little bit of presentation of my book on conceptual spaces. So I talked already about the symbolic models, where you have predicates or variables in a programming language. you suppose you know what these variables means. It's the programmer who puts meaning, or the logician who puts meaning to the variables. And then you have all kinds of operators, logical operators or programming operators. But one problem for this tradition is, where do these predicates come from? I mean, where do we, and very often it's humans who put them in. Then we have the connectionist models, machine learning models. I already talked a little bit about them, but you have then distributed representations by dynamic connection weights that are changed by learning and so on. But they can solve categorization problems, but we never really know what's represented in the network. You have to extract that by fairly complicated methods. And learning is in general very slow. I mean, you have to train and train these, you know, if you want to have a fairly complex result, or a stable result, I should say. And these are done on a rather low level of representation. This is on a linguistic level. What I put in here is my conceptual spaces that are on the middle level of granularity, if you like. So this is a form that is based on geometry, vector spaces and convexity and things like that. And I will give you examples of what I mean by quality dimensions. But as I say, here the main core is a geometric structure. I mean, you can extract some kind of geometry from these systems, but that's normally not what people do here. So I assume that we have some kind of dimensions given. But what the problem I don't solve is, where do these dimensions come from? And if we talk about human cognition, human perception, we know that we learn oh, I see. It comes later. We learn to extract information about space and time and weight and color and so on from our perceptual mechanisms. But when it comes to artificial systems, it may be a little bit different to how to extract the relevant dimensions. And I'll get back to that problem. Okay. I already said this, that formal ontologies are still based on first-order logic. And what you have in formal ontologies is very often an attempt to classify all animals or all chemicals or all things like that. You have hierarchies. I mean, the hierarchies are the core idea of a formal ontology, hierarchies of concepts. But the concepts that you study are very often nouns, what we represent in language by nouns, or adjectives, properties of concepts. What is missing here is very much actions, and what we represent by verbs in language. If you think about the symbolic representations, they are based on predicates. And predicates, you don't make any distinctions between these predicates. The predicates can represent nouns, they can represent adjectives, they can represent prepositions, they can represent verbs. Predicates take everything. I think that's a mistake. I think that the system should have some kind of way of categorizing. And formal ontologists try to do that, but they somehow, some people try to model actions, but I still think they are not very cognitively realistic. And they are not grounded in perceptual system. I mean, this is the grounding problem in AI. We miss them in the formal ontologies. Another thing that I was working very much with when I was doing the concept models in the conceptual spaces is that we as humans use similarities when we categorize things. In neural networks, you take into account similarities. But in these formal ontologies, they don't show up. So that's another limitation, I would say. And if we look at what's happening in current AI systems, there is a focus on categorization. So we have all these deep learning systems that can categorize faces or objects. They can outbeat humans in classification. But they need lots of examples to train, and we don't really know how to do the categorization. And again, they generate data for nouns and adjectives. The verbs are missing in these systems. Actually, the new deep learning systems, they contain not very much new theoretically. I mean, they're basically doing the backpropagation system from early network systems. So some people have called it, this is deep learning 2.0. What we have now is quicker computers and larger training sets. larger data sets. But theoretically, there is very little new in these deep learning models. Yeah, this is what I said already. Contents or concepts are opaque in neural networks. We don't really see how they are represented. And above all, deep learning is very little reasoning. There is no planning, nothing. I mean, it's almost always categorization. So I think current use of the term AI means categorization systems. That's what deep learning is. And I think that's a very limited notion of AI. I want a system that can plan and reason and take in information and so on. Otherwise, it's not really an AI system, in my opinion. So this is my proposal, the event structure as an appropriate ontology. So now we go to back to the conceptual spaces that I want to use as a base here. And they organized in, information is organized in quality dimensions. And they are sorted into domains. So space has 3 dimensions, time has 1 dimension, temperature has 1, weight has 1, color has 3 in human perception. Shape, we don't really know how shape space looks like, but we know that a cup is more similar to a glass in shape than it is to a chair. And I want to make a kind of announcement for force space. We are quite good at handling forces, and I'll get back to that. So forces are important here, in particular when it comes to actions. Dimensions within a domain are integral. That is, we can measure the location of a thing. They are hanging together. The color dimensions are hanging together. There are psychological tests for this. I don't want to get into the details here for how these dimensions are grouped. But in mathematical terms, it means that they come with a common metric. So ordinary space is a Euclidean space. Color space looks like this. I mean, I'll get back to that. It has a different topology. And the domains have different topologies or metrics. You can represent similarity in these spaces by distance. The closer 2 points are in a space, the more similar they're supposed to be. And then this is my criterion here for what a concept is. A concept is a convex region in some space here. And a simple way of illustrating this is my standard color space here. This is human perception of color. There's a dimension called hue, going from red via blue to green, yellow, and red again. This is circular dimension because you can talk about opposite colors. And then there is the intensity, going from gray and out to more and more intense colors. And the third dimension is brightness, from white to black. These 3 dimensions are not independent, because when you get close to white, when you get very light colors, it's more difficult to distinguish a light pink from a light yellow. So you have less discrimination there. And distances in this space is supposed to represent how well we can discriminate color. So there are psychological experiments based on color discrimination that generate this space. And then, as I said, on this space we can then talk about what is the meaning of the word red. Well, in my construction here, it's a convex region of the space. I mean, it should actually be a 3-dimension because it goes a little bit into the light area and a little bit into the dark area. But I can't draw in 3 dimensions, so it's just, yeah, okay. So this is the meaning. So my hypothesis is that all color words represent convex regions in this space. And this has been confirmed later by linguists. I mean, this is different languages carve up the color space in different ways. Some languages have very few color words, some have many, but almost without exception, all color words represent convex regions of this area. So this is my hypothesis, that the convexity or within a domain is what characterizes concepts. And that's actually an important factor when you want to learn things. Because if you learn things, exemplars of red or some concept of birds or something, then you know that if you've seen this concept, this instance and that instance, then you know that anything in between is also an instance of the concept. So convexity helps learnability of concepts. So that's a feature that makes it, helps to give this representation a quicker learning than what you would find in neural networks. Now, the group in Palermo and Sicily, Antonio Keller and so on, they applied this kind of distinction between three different levels, as I talked about, the neural level, the conceptual level, and the symbolic level. So they developed a system for artificial vision. So you have a video camera, you make, and they were influenced by David Marr's representation, you make a 2.5D approximation of it, then you get a viewer-centered mental image, then you get a 3D approximation of the system. This is done on a neural network basis. Then you have some kind of representation of it in a spatial domain, in some kind of conceptual domain. That's the middle level here. And then you can put names on the things. You can talk about whether it's a cup or a bottle or whatever they are classifying here. And then you have a symbolic knowledge base where you can represent these meanings. And so you have a system that goes between these three levels. So their architecture was actually based on this, having a neural network at the top here, and then having a symbolic representation at the bottom, and then in between they had this kind of conceptual representation in a space. So that was the first example of an AI system that really used this kind of architecture. What I'm proposing is something that looks like this, and I will get back to it, but I would just want to say that we are thinking, this is the work I do with the people in Sydney. So we're thinking of having three different processing systems, three different modes of representation of information. So here's the neural network that does this categorization stuff and so on. Here are the conceptual spaces where you can locate them as region. You can talk about relations between concepts. You can talk about similarities and so on. And here is the symbolic system. And this looks like a blackboard system because these systems are then supposed to connect to send information in and out to this event board. And I want to say something about that. This is not just a blackboard. I want to say what I mean by this being an event board. And then there is a control layer with all kinds of systems. I'll get back to that at the end. But basically, this is a pipe dream. I mean, my AI system contains all these forms of knowledge representation. But they are communicated via not just a blackboard, but a system that's constrained by event structures. So now we are... I want to say something about this. So low-dimensional outputs from the machine learning layer can use to define correlations between categories or causal relations. I'll talk about causes in a while. And then they're represented as on the symbolic level as sentences. And the correlations can function as constraints on the learning process. You can have this, top-down from the symbolic or conceptual level to formulate constraint on the subconceptual level. But the new idea, which I think I haven't seen in AI systems before, is to use events as the common form of representation. So, event semantics. That's something that has been studied quite a lot in linguistics and in psychology. People have been doing all kinds of experiments on how we perceive events. And we categorize events in terms of different roles. Linguists call them thematic roles. So you have somebody who is an agent or something that is an agent that is creating an action. There is a patient. I mean, if I'm lifting the cup, I'm the agent and the patient is the cup. And the action is my lifting, and the result is that the cup is up in the air, and there is no recipient here because I'm not giving it to anybody. But that could be a third role. And there could be an instrument. I could have used some kind of instrument to lift it, or if I use a pen to write, that's an instrument. So these are what's called thematic roles. I'm focusing on the first four here because they are the central ones: action, patient, action, and result. And when we categorize events, we assign things like this. I mean, if I'm hitting somebody, you immediately know that I'm the agent and the other person is the patient. We know intuitively our systems, our mental systems, are categorizing the world in these categories. So I want to say that these are very important categories when we understand the world. And I think that an AI system, at least an AI system that wants to communicate with humans, should have these categories as well. And if you have this, if you see somebody suddenly get a tomato in his face, then you expect, or you form some kind of inference that somebody has thrown the tomato. If you see something falling down from, well, okay, that's not a good example, but we always, if we see some kind of result, we always expect that there is some kind of cause of the result. This is the causal thinking. So the action is then the cause here. Or if I drop something, you expect, you don't see it, but you expect that this thing I drop ends up in a certain location. So when we see parts of an event, we have expectations about what is coming. And these expectations can be formulated in terms of patient, action, result, and so on. And that's a very natural way for us to reason about in terms of this. We sometimes make mistakes, but that's, well, it's a core of planning, as I'll get back to. And that, yeah, our expectations control attention. If I drop something on the floor, I don't start looking for it up there because I know that the gravitation brings it somewhere here. My attention is drawn to the floor. We have, so attention is another variable, and that's actually part of the control layer of our system. But the attention, well, we can, of course, if I'm planning something, I may attend to something, a timetable or something, information about the space or whatever, that gives me the information I need for my planning. So I can generate the attention myself, but it can also be controlled by events in the external world. So this is a model I developed together with an economist, Massimo Vaglia, of how we describe an event more formally. So it's one agent, some kind of object, animate object, or a physical object. But it's an agentive thing. It's something that can exert a force, something that can create forces that generate. So when I'm lifting things or moving around, I'm using my bodily forces. And that is described by a force vector, or sometimes by a force pattern, more complicated thing. And then there is the patient, an object that we can represent in a conceptual space, having this or that properties, that has a location, that has a color, blah, blah, blah. And something happens to the patient. It falls down, it gets hurt, it's painted, it's heated, something happens to it, it moves, and that's the result vector. And the result vector is then described as a change of the properties of the patient. So each of these components are represented in some kind of conceptual space formalism. But this is the basic structure that we see of events here. So the force vector acts on a patient, comes from force space, generated by an action. Not always. I mean, we always have gravitation as a force in our lives, and gravitation generates some kinds of events or results as well. And the result vector then describes the changes of the properties of the patient. It can be changed in location, or it can be change of the property of the patient. I mean, whether it's heated or painted or destroyed or whatever. And sometimes nothing happens, and then the event is a state. The cup is on the table. I mean, there is a stable balance between the gravitation and the upwards forces from the table. There is no result. There are a couple of force vectors involved, but it's in a state. The cup is on the table. Sometimes the agent is identical with the patient. I can do actions on myself. I can walk, I can jump, I can scratch my head. I'm the patient as well. I exert forces on myself, so that's nothing. Sometimes that doesn't have to be an agent. If we have falling, for instance, or growing, or dying, I mean, then it's something that goes on within the patient without an agent going on. I mean, gravitation is not an agent as such. It's just a force. Okay, so that's the basic structure of an event, these four components. Then you can add an instrument, you can add a recipient, you can build out this model, but this is the basis for the modeling here. So here's a very simple case. This is the agent, this is the patient. This is the force vector you're pulling in this direction. This is the result vector. The result is that the sled is moving up this mountain or hill. The force vector is not parallel to the result vector because there are other counter forces, in this case mainly friction, and of course gravitation as well, that makes the connection between the result vector and the force vector a little bit complicated. So we have to model the counter forces as well, but I haven't included them in the model here. Yeah, so force is typically the cause, and result is typically the effect. So via this event model, we get, I shouldn't say for free, but we get a causal relation built into the system. And very few AI systems that I have seen, I mean, some people have tried to model causation within propositional systems. And I'm a bit skeptical that they will work. But here, once you have the vector, distinguish between force vectors and result vectors, you have an automatic distinction. And by the way, most philosophers think that causes and effects are the same kind of entities. I think that's a big mistake. I think that causes are somehow related to forces, and effects are then related to changes of properties somehow. So we make a distinction here between that. I've already said that. And Judea Pearl, who has done lots of probabilistic causal reasoning, he says that in order to have a good learning system, artificial learning system, that reaches human level performance, we need learning machines with causal reasoning tools. And I think he's perfectly right. The question is, how do we put these causal reasoning tools into the machine? And so I'm proposing something here that would give us some form of causal relation once we have modeled the action, the force, the patient, and the result. And linguists talk about sentences as being some kind of unit in a language. We all identify sentences. Very few people have said anything about why is a sentence a unit. Why is it a cognitive unit? Well, my simple answer is that a sentence describes an event. Maybe a state, but an event. So that's the point. I mean, you have a sentence expresses not the total event, because the world is very complicated, but we pick out, we focus on certain force or a result vector. A sentence doesn't have to have both of them, but at least one representation of a force or a result, and that's the verb phrase. And then we talk about either an agent or a patient or both, or sometimes more people or more objects. So a sentence combines elements from this event model. So patients and agents end up as noun phrases in a sentence. And force or result vectors end up as verb phrases. So once you have this division between the agent-patient on the one hand and the force result on the other hand, you get this basic linguistic division between noun phrases and verb phrases automatically. It comes out from this model. And of course, you can't say in a sentence, you don't say everything about what happens. You focus on certain aspects. So it's, linguists call that you make a construal of an event, and then you express this construal. So here attention comes in. I mean, I can focus on let's say, different parts of an event. I can say that I hit the cup. That's a sentence, and I can say that the cup fell down or the cup broke. In the first sentence, I'm saying, me, the agent, force vector hit the cup, the object. In the second sentence, I'm focusing on the cup and the result, what happens. It's breaking or it's falling down. We also have different ways of focusing. I mean, in an active sentence, Victoria hits Oscar. She is the agent, and here's the patient. Now, here's a passive sentence, but Oscar is still the patient, and Victoria is the agent. But now, in this construction, we are focusing on Oscar. So it's a different attention on the participants here. Here is a picture of a system developed by Peter Ford Domine in Lyon, together with his group there. And he has developed what he calls reservoir computing. It's a kind of neural network, but the neural network is structured. So you have, he takes a sentence. What is the sentence? John was hit by Mary, almost my sentence. He has a lexicon where4 of the words are mapped into. Then there is this neural network that classifies this into, he has got four categories here. The predicate, the agent, the object, the recipient. What distinguishes his model from the model I'm proposing here is that he's not dividing predicate into action or result. So what I had an EU project where we collaborated, and I convinced him to make a little bit, add this division of the predicates into actions and results. And I'll give you an example of what happened. And then you can learn these mappings between the words and the places in the sentence and so on. And he's been quite successful in getting some form of, you give a sentence as an input, and an output you get the classification into these roles and what's going on. So it's a kind of semantic analysis of the input. So let me give you an example of what we did together. Here is a, come on. So this is an iCub robot. So then I should turn up the sound if you can hear something from it. This is a PhD student, Anlo. So she is giving a command to the robot, and he is interpreting it. Push the crocker. Human says it's all right. Now he's thinking about it. So he's got 2 things. First point crocker, no, point cube, then proof crocker. So now he's pointing, and he's not very good at pointing. And then the second action is push the crocker. And he's not very good at pushing either, it is iCub, but it happens. Now comes the interesting part. She asks questions here, Anne-Laure Mellier. Oh, that's the robot, the iCub. So what did you do? And he's asking for the action here. I pointed to the cube, and then what happened? Crocker moved. This is a result of what's going on. So this iCub, pushed by me, that's an action. So her question are formulated. So she asks either for an action or for a result. How did you do it? What happened? And the robot has learned to know whether it should talk about the action it performed or what was the result. So we have made this distinction. And you see that it's not a very advanced interaction, but still there is some kind of understanding of what's going on. And the speech perception of this robot is quite good. I mean, it picks up the French accent without any big problems here. So that's not bad. Now, I was complaining about, let's see now, we should talk about verbs. Yes. So I was complaining about that AI has not really studied verbs, as how to represent verbs. So I have made an analysis of different word classes. And for me is a verb. There are 2 kinds of verbs, but it's a complex regions of vectors. I mean, for me, it's either the force vector or the result vector that the verb represents. So it's a complex regions of vectors that depends only on a single domain. So the verb to push something, that's a force vector generated by the agent and with a certain direction. So that belongs to the force domain. Then we have move, which is a result. I pushed the table moved. So that's a change in the location of the object in the spatial domain. And then I could say I heated the soup. And what happens then, the result is that the temperature of the soup changed. And I have this thesis that all verbs refer to a single domain. To forces, to heats, to weights, to colors, whatever. I mean, so we can discuss that, but that's a thesis that verb meanings relate to single domains in conceptual spaces. So, as a consequence, there are no verbs in natural languages that mean walk and burn, because that's 2 domains. There are no verbs that mean crawl or run, because that wouldn't be a convex region of action space. There could be verbs that mean run or jog. There could be verbs that mean walk or walk or run, because they are fairly similar as actions, and they could be covered by a certain region of action space. I haven't given you the details of an action space here, but this is the patterns of force vectors we are performing when we are acting. So, yeah, and I want to make a distinction then between manner verbs that refer to actions and result verbs. And linguists more or less agree. There is a little bit of a fight on this, whether this is a 100% distinction or whether there are good exceptions. But basically, all verbs can be classified into manner verbs, describing how you do something, like pushing or hitting or kicking or whatever, on result verbs. That describes changes in location or changes in properties. And I think that this distinction is important for AI, because if you look at AI systems that include verbs, almost all verbs are result verbs. So the AI people have focused on result verbs. But I think we need to get into the action verbs as well. And I had a former PhD student, Sarah Garé, who was developing this. So we have, this is a neural network system. We take a Kinect picture. You know what Kinect is, this camera that picks out a skeleton. And that's the input. And then there's a pre-processing. We get a scaled and viewer-centered or viewer invariant representation. Then there is a self-organizing map that classifies these actions. And then there is an output, which is a linguistic output. So let me show you. Yeah, OK, here is an example. So this is a summary of the Kinect data. There is a person who is catching something with a hand. You make this kind of movement. This is a waving your hand. They're kind of similar, but the temporal pattern is different. Hammer is then doing this kind of thing. And high throw, draw X. These are 6 different hand movements that you can make. Draw X means doing like this. Yeah. So we took movies of people doing these things, and then we trained the neural network on classifying them. So I'll show you an example of how it works with Sarah's work here. No, sorry, I didn't get it. Yeah, I'm sorry. OK, we have to do with one of these then, without seeing. You don't see the human performing the action. You only see this, and this is in slow motion. So you have different output neurons here. They all represent different actions. And then this is the desire. The figure is doing a front wave like this. And then as the system goes through, you get different guesses. So you get the guess front wave here after some period. So we could train a system to distinguish between 10 different hand actions by using this Kinect. And Kinect is not a very stable system. Sometimes the body parts flip around a bit here. So this is draw a circle, and it gets it right after a part of the movement. So here we are using a neural network to classify actions, to get manner verbs out of the system that we would need for an event representation, where we would need to understand the force vector. So yeah, sorry about that. OK, now I've given you some of the parts that I think would go into this system. So on the event board, you would have these patient-agent manner result representations. We would categorize the input data here. And then we can start reasoning about them. We know things about the relations between causes and effects here via the connections between the actions and the results. The input, I mean, I showed you how we would use a neural network to classify an action. But of course, you would use neural networks to classify objects as well, and so on. So the classifiers come in there. And then we have representations in these spatial domains. Then we can turn them into linguistic representations and start reasoning about them. So there is input, taking care of that. There is simulation. We can run systems without contact with the reality. I have simulations of in planning situations, for instance. There is a control system. There is a system controlling the attention of the system. And the attention depends on the goals of the system, what you want to do. And then there is, of course, some kind of output. Output is either sentences or actions. And input is similar. That's, okay, I say a little bit about the control layer. Input is perception of sentences. Output is action or sentences. Control assigns tasks to the procedures. Attention biases these assignments, and the simulation can be used for planning tasks. So, this is the general architecture of an AI system that I'm proposing. And what is new here is that I think that by looking at how humans handle events, and by using the kind of event model that I've been talking about, that is semi-formal. I mean, we have these vector representations and so on. We could do AI systems that are cognitively more realistic, more related to how we as humans solve the problem. I'm not saying that this is the only way of doing AI systems, but we want to have a system that communicates with humans. I think this is a way to go. As I said, a lot of hand-waving, no concrete results. I showed you a little bit of what we've been doing with the group in Lyon and what I've been doing with action recognition in Lund. But all these pieces have to be put together, and nobody has done that so far. Thank you very much.